Everybody, video notes 3-2. Today, here's the 4 bullet points of objectives we're going to be learning. A lot to look at in the book. Okay, look, you can get bonus. Do this. Do this. Do this. It'll help you learn. Okay, I'm on your side. Give you something to do that'll help you learn. So let's review. Covalent bonds, we learned in the last one, means electrons are being shared. Oh, look, they're sharing. So 2 nonmetals are involved. It's called directional covalent bonds because they're shared in the direction in between the atoms. Covalent bonding usually fills an octet, except hydrogen, when it bonds, only needs 2 around it, and boron only needs 6. So here's 2 nonmetals. Remember, hydrogen acts as a nonmetal. And so one way to represent the sharing going on here is sharing those electrons. Okay, covalent bond sharing. Okay, so how do you know if a dot structure is good? Check it out by counting the total valence electrons. So if there's, so let's just do NH3 again, right? Nitrogen brings in 5, hydrogen brings in 1, and there's 3 of them, so we need a total of 8 electrons in that dot structure. So when you do this, and then this, there's 1, 2, 3, 4, 5, 6, 7, 8. And then you change all of the pairs that are being shared to lines, and you still have 1, 2, 3, 4, 5, 6, 7, 8. All right, brought in 8, using 8. Check for octets. Okay, so nitrogen, let's count everything around it. 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen thinks hydrogen's great. Okay, now remember that hydrogen only needs 2 around it to be stable. So this hydrogen has 2 around it, so it's stable. Okay. Finally, multiple bonding. You only use a multiple bond between carbons, a double bond or a triple bond. I said carbons between atoms if you run out of electrons. One example is this. If I bring oxygen, 1, 2, 3, 4, 5, 6, with another oxygen, 1, 2, 3, 4, 5, 6, they make a bond, right? And with that bond, this has 1, 2, 3, 4, 5, 6, 7. So this oxygen is not stable yet. I cannot put any more electrons because I've already used the 6 from this oxygen, and the 6 from that oxygen. So I can't put any more electrons in. But I have unstable atoms. So if these electrons get shared between them, you have to erase them. So, oh man, I gotta erase them, because I'm redistributing them to be a bond. Okay, so now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total electrons. That's how many that came in. 2, 4, 6, 8. That oxygen's happy. 2, 4, 6, 8. That oxygen's happy. So that's how you make sure a dot structure is good. So dot structures for ions. Charge. There's 2 kinds of charge. You can have extra electrons. That's a negative charge. Or you could have not enough electrons. That's positive charge. So a single ion, this is an F -1. So fluorine brings in 7 of its own electrons, 1, 2, 3, 4, 5, 6, 7. But an F -1 has an extra electron, and so we put brackets and put the charge on the outside. Okay. Sulfur -2. Okay, it's called sulfide. It has 6 valence electrons because that's how many it brings in. 1, 2, 6. A -2 charge means it's got 2 extra electrons, so it's a -2i. A magnesium atom is Mg, 1, 2, because it's got 2 valence electrons. A magnesium ion, a +2 charge means, oh no, I lost something. Are you sure? Yes, I'm positive. I lost it. I'm positive I lost it. So magnesium ion would look like this. Okay? No dots around it because it lost 2 electrons. Polyatomic ions. Poly means many. Atomic ions means lots of atoms in this ion. Okay. Here's an example. OH-. So the O brings in 6 electrons. The H brings in 1. Okay. But this means there's an extra electron. So we have a total of 8. So never fear, the train's coming by. Probably 6. Right. And hydrogen brings in 1. Right. So you make this bond. And then that takes care of 1, 2, 3, 4, 5, 6, 7. Oxygen's not stable yet. Hydrogen is stable. Okay. So this extra electron is probably going to go right there. And so now we have stable atoms that all the electrons are accounted for. This is the extra electron went right there to make oxygen stable. Okay, so bonding. There's a continuum of bonding. Right now we're talking about covalent, but it goes from ionic to covalent. It's a continuum. N means electronegativity difference. So if you subtract the difference of the electronegativity of the atoms, and the difference is 0.4 or less, then what you have what's called a nonpolar bond. What is a nonpolar bond? It means that the atoms are sharing their electrons equally. No poles or differences are created. So this is an atom, this is an atom. They have about the same electronegativity, so the electrons that they're sharing are evenly distributed between them. Okay. Now, what if you have two atoms that are not sharing equally, meaning that their electronegativity difference is 0.5 to 1.9. Okay. That means that they're sharing electrons, but the higher electronegativity gets more of the shared pair. So there's poles created or opposites, kind of opposites created. Okay, so here's two atoms sharing electrons, but this atom is higher electronegativity, so it pulls the electrons closer to its side of the bond. This side of the bond is kind of positive because it's lower electronegativity, and so the electrons are being pulled away from it even though they're sharing. Okay, sharing. Okay, unequally. This is sharing equally. Okay. So this is nonpolar. This is polar. So what does ionic mean? Well, that means that the electronegativity difference is so big that the atom that's higher electronegativity, lower electronegativity. So guess what? The electrons get taken away from the lower one. It turns into a cation and an anion. That's transfer of electrons from low to high. Okay. So let's practice. What's the diff? That's what we're asking. Difference in electronegativity. So here are the cutoffs to help us decide what kind of bond is forming. So let's see what's the diff with NO. Well, here's N, 3.0 electronegativity. Oxygen, 3.5 electronegativity. Now I'm going to say, what's the diff? The diff is 0.5. Now you might be saying, hey, that's negative 0.5. Well, it's always bigger minus smaller. So it's absolute value. Right? And so then 0.5 is the difference. So what does that mean? That means that an NO bond is a polar covalent bond. Hey, look, she's writing small. Okay. FF. Well, let's see. 4.0 is the electronegativity of fluorine. And 4.0 is the electronegativity of fluorine. Subtract them and you get 0. What's the diff? The diff is 0, so this is a nonpolar covalent bond. So that means those atoms are sharing the electrons equally. Okay, PB and F. PB is 1.8. 4.0. What's the diff? All right, so 2.2. 2.2. What does that mean? It's an ionic bond. All right, so the electrons get transferred to the fluorine. CH, what's the diff? 2.5 and 2.1, 0.4. What does that mean? Well, 0.4 is nonpolar covalent bond. That means C and H share electrons equally. Nonpolar covalent bond. So you can decide what kind of bonding atoms are going to do based on electronegativity. That's one way to do it. Okay, so just to re-emphasize what that means. Nonpolar covalent, look at those two little guys, they're sharing pretty equally. It's going to be two nonmetals in the bond, and the electrons are shared evenly, and so the electronegativity difference is a small difference, 0.0 to 0.4 is the difference. Most elements that are diatomic or carbon bonded to hydrogen are nonpolar covalent. Oh look, it's H2, hydrogen bonded to hydrogen. They're going to evenly distribute their shared electrons between them. Because what's the diff? 2.1 minus 2.1 equals 0. No difference. Equal sharing. Iodine is I2. Okay, so what's the diff? Whatever iodine minus iodine is going to equal 0. What's the diff? 0. equal sharing, so the electrons are evenly distributed. Okay? Even distribution of electrons in nonpolar covalent bonds. What about polar covalent bonds? Well, they're sharing. Co means sharing, right? So you have two nonmetals again, usually, and it's called a polar covalent bond because there's uneven sharing. Why could there be uneven sharing? It's because one of the atoms in the bond is a bigger hog of electrons. It has a higher electronegativity. Hog of electrons. Okay. So the one with the higher electronegativity pulls the electrons they're sharing closer to itself. So here, look, these two atoms can share electrons, but the chlorine is more electronegative, so it pulls the shared electrons towards itself. Okay. Because one side of the bond is pulling the electrons closer to its nucleus, that side of the bond is going to be kind of, that's a partial sign, negative, leaving the other side kind of positive. This creates what's called a pole, and a pole has opposite charges, okay? And another word for that pole is called a dipole. Dipole. Okay? So the partial, this is a Greek letter delta symbol, represents the partial charge on each side of the bond. Oopsie, I want to put bond. Okay. Oopsie, now I want to erase that because guess what? I'm going to put something else there. All right, so I'm going to cross out molecule. Cross out molecule and put bond. The partial charge symbol, or that's a Greek letter delta, represents the partial charge on each side of the bond as indicated. Okay, so this is a kind of negative, that's kind of positive. You could also use an arrow. Okay, the arrow always points to the kind of negative, and the other end of the arrow is kind of positive. All right. Hey, it's a no bond. No. All right, so we checked a no bond back here. We found out the difference is 0.5. All right. So this was a 3.0, and that was a 2.5. What's the diff? 0.5. All right. So, I think I did that wrong. No, I was 3.0 and 3.5. Come on, Harbin. You can do this. 3.0 and 3.5. So what's the diff? 0.5. So which of these has the higher number of the oxygen? So we could put a partial negative sign on that and a partial positive sign on that. Or we can draw an arrow pointing to the negative side. This is called a polar bond. Polar bond. And this is called a polar bear. Cute. All right. Where do you find polar bears? Okay, I know this is not as accurate as it could be, but at the poles. So polar bonds mean they have poles. Okay. So what if you have a molecular compound? Then you have two nonmetals. So you have to call that molecular compound something. So when we name the molecular compound, we use these prefixes to tell us how many of each atom. So if there's one atom, we say mono. If there's two atoms, we say di. 3 atoms, tri. 4 atoms, tetra. 5 atoms, penta. I think you get the pattern. And they keep going. Octa means 8, nona 9, and deca 10. Okay. The second word of the molecular compound ends in the suffix IDE to make it sound good. Second word ends in IDE. So what the heck am I talking about? Well, let's look at a couple. Look, it's SF6. Nonmetal, nonmetal. This is a molecular compound held together by covalent bonds. So we don't use mono on the first, so keep these rules. Hey, do you know what CO is? CO is carbon monoxide. All right, so that's your guide. This is called carbon monoxide. All right, so what kind of rules do we use here? Well, we don't use mono on the first if it's a mono. We use a prefix every other time. And we always use a prefix on the second word, and we don't put double O's. So, nonmetal, nonmetal. It's a molecular compound held together by covalent bonds. So we name the first one sulfur. We don't need a prefix. Why? Because we don't need mono on the first. But we do need a prefix for the second one. We're going to use hexa, because that's what 6 means. Fluor. And then I'd change the ending to IDE because it sounds good, and the suffix ending is IDE. Oh, look, it's phosphorus. Phosphorus. Okay, and I don't need mono on the first. And then it's 5, so it's penta. That means 5. And then chlorine is the element, but it sounds better to change it to IDE. I'd change it to IDE, second word. Oh, look, it's 2 nitrogen. So this time, since there's 2, we have to say di. You don't use mono on the first, but you need it on. Dinitrogen. And then we have 4 hydrogens. 4 is tetra. Oh, hey, spell it right. Tetra. Tetra. And then hydrogen turns into hydride. Dinitrogen tetrahydride. Oh, look. It's dinitrogen. I said nitrogen. Who calls that nitrogen? Try again. Dihydrogen. 2 hydrogens. Okay. How many oxygen? 1. Hey, come back. Monoxide. Alright, so these are how you name these. How do I know to name these as molecular compounds? Non-metal, 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 non-metal. Oh, look, it's the name of a compound. Trinitrogen monosulfide. Trinitrogen. N. Tri. 3. Monosulfide. Sulfide comes from sulfur. Boom. Mono. Done. Trinitrogen monosulfide. Hexasulfur. 6. Sulfur. S. Dichloride comes from chlorine, which is Cl. Cl. Di. 2. Okay. Decanitrogen. Whoa! Deca. That's 10. Monoxide. N10O. Crazy compound. But that's how you would name it, because the prefix, the symbol, the number, prefix, IDE at the end. Alright, so just to review. Hey, let's put the sharing sign on. Covalent bonds share valence electrons. Unevenly is polar. Evenly nonpolar. Kinds of covalent bonds. Polar, nonpolar. Polar bonds. Point the arrow towards the hog. Right. Partial negative, partial positive. Nonpolar bonds. No arrows because there's no partials. Right. How can you predict which type of bond is present? Well, we can talk about the properties. We can talk about the electronegativity difference, and we can talk about the types of atoms in the bonds. Alright, so I told you about the book. Make sure you read and do this, okay? Seriously, do it. You'll get to see some cool stuff in the book. Alright? Alright. Can you do this? Okay. Draw loose dot diagrams. Octet 8. Alright. I heard 18. These are multiples of 3. Alright. I'm going to stop now. Peace out.